A standard feature of cryptographic algorithms is the use of keys. So if a transmitter and a receiver are sharing a key, for example, in some cryptographic algorithms, this means that it's very difficult for an attacker without that same key to be able to decrypt the message sent from the transmitter to the receiver. There are two main models for how these keys are related. In the first model, known as shared secret cryptography or symmetric cryptography, the two keys K1 and K2 are the same key. That's reasonable, makes sense, and it's easy to see why then if the attacker does not have the same key, the attacker might not be able to decrypt the message, because the key is what unlocks the message. There is, however, not just this model, but another model where the two keys are still related but they're not the same. They are in fact different keys, albeit related keys. This is the public key cryptography model, also known as asymmetric cryptography. The reason it's called asymmetric is that the two keys are not the same, so it's not symmetric, whereas in the case of symmetric cryptography, the two keys are the same. So let's take a look at shared secret cryptography first, and then we'll try to explain why people use different keys in public key cryptography. So in shared secret cryptography, we have actually not just in shared secret cryptography, in both shared secret and public key, we can look at this diagram. We have Alice wanting to transmit to Bob the message, unencrypted message M, passes through a transformation T, together with the input of a key K1. This produces the ciphertext C, which then goes to Bob, and that passes through the function U that is unencrypting and resulting in M being received by Bob, the message M. So the function U needs to take the key K2. It's easy to see why with shared secret cryptography you share this common secret, so the two keys are the same, and then in a sense U is just reversing what T did. On the other side you get back M. What about with public key cryptography? In the case of public key cryptography, K2 is the private key of Bob, and then K1 is its public key. So the public and private key are related. Very interestingly, the public key K1 can be freely distributed and widely known without affecting the security of K2. So you're not able to derive K2 just by knowing K1. And without compromising the security such that just because someone knows K1, they might be able to eavesdrop. It's more about having K2 that allows an attacker to be able to decrypt successfully. So the attacker doesn't have it. At most, the attacker might have K1. So this is very useful in the sense that the key K1 can be published, and Bob doesn't have to spend a lot of time to go arrange shared keys with all the devices that Bob wishes to communicate with, Alice and others. But you still have a key management problem, because how does Alice know, for example, that the key K1 is indeed the public key of Bob, right? So then but at least it's useful to have different keys, so that now you only need to keep K2 private. A disadvantage though of public key cryptography is that it's computationally more expensive. So one popular way that it's used is that it's used to derive a shared key between a transmitter and receiver, following which the actual data communications would be encrypted with that derived shared secret. What about in Wi-Fi? Which of these two models do we see? In WEP, we see a shared secret. In WPA, also. WPA2 PSK, which is WPA2 pre-shared key, also uses a shared secret. However, WPA2 enterprise mode may or may not use public key cryptography, depending on the specifics of the protocols actually used. So it has that possibility.